Hello everybody, my name is Mikolaj Pawlikowski. I'm the author of Chaos Engineering Crash Test Your Application book for money. And this is literally the first time in my life that I'm trying to do a live stream, so yeah, go easy on me. We're going to focus today on one particular chapter from the book about Docker. If you're curious or if you've never heard of Chaos Engineering before, this is the book that I'm talking about. It's currently on early access. The first 4 chapters, you can access them, I think, for free right now on the website. And we'll be talking about Chaos Engineering, Docker, a little bit today. During this time, I'm going to be using a VM that comes with the book. If you click on the manual website, if you go to Show All and click on Source Code at GitHub, you can see the repo in which you can basically download a VM that has all the things pre-installed in order to do the exercises that are included with the book. The instructions are attached to every release. Currently, this is all in pre-release because the book is not finished yet, but just pick the latest one, and if you go into the assets, there's going to be a few files that you need to download, and then just follow instructions here to get everything set up. It's Ubuntu-based VM that comes with some pre-config, that comes with all the examples and all the exercises from the book in it. And to run it, the easiest way is probably to just use VirtualBox. So I'm going to be using that in the presentation today, and you're free to download it. It's probably the easiest way. Okay, so we're going to be talking about Docker today, and I just wanted to kind of start. It's a little bit tricky because I'm going to try to spend between an hour or 2 with you and kind of show you a little bit around making as few assumptions about your knowledge of Docker or the containers technology as possible. I'm also realizing that the streaming software is pretty harsh on my MacBook. I didn't expect that to happen, so I tried to tweak the audio settings in a way that you are going to be able to hear it. Hopefully that worked. All right, so if I was to kind of describe what my goal for today for the session is to kind of give you a sneak peek preview of what you can expect to see when you buy the book, and kind of grasp your interest to see how the chaos engineering can be applied to Docker, both to test the Docker itself or to verify the assumptions about what you think is going to happen to Docker in certain circumstances, and also to test your applications later on. So let's just start with a little bit of what Docker actually is. I'm assuming that you're familiar more or less with, you've at least been using Linux for some time, and you've probably heard of Docker. It's kind of hard to miss. It has this nice logo with the whale. It's very cute. But underneath, this diagram shows you what it's actually based on. It kind of, stands on the shoulder of giants. And to implement the containers, it's leveraging a whole bit of technology that resides in the Linux kernel. So if you are asking a Docker to start a container at the top, Docker itself is leveraging either LXC or used to, and in a bigger way now libcontainer, to interface with the Linux kernel. And inside of the Linux kernel, there's a few technologies that the whole thing relies on. There's the chroot, that is basically a syscall that is responsible for changing what the root of the file system looks like from the processor's perspective. There are the namespaces, which control the isolation of what the process can see. For example, in terms of PIDs, we're going to take a look at that in a minute. But basically kind of categorizes what your process can see, and what is tricked into thinking is the reality. We have the C groups that limit the access to a specific set of resources. For example, we're going to take a look at how it's used to limit the RAM available to a container as well as CPU. We have the seccomp that is a mechanism for essentially limiting what system calls a particular process can make. And with other things like SELinux and AppArmor, there's this entire security aspect that can be implemented. There are the capabilities that grant privileges that basically before capabilities, the super user could do everything and the user couldn't. And with capabilities, it's kind of broken down into smaller pieces that you can grant access to a particular user to do. And then there's networking, in which case there's a few different options that can be leveraged. And the file systems. And the file systems are interesting. We're also going to take a look at that in a minute, because Docker leverages UnionFS or similar file systems that allow for an efficient way of storing the data if you're using a lot of containers that share different things, share the same files rather. So this is like the high level overview of what bits are involved. And inside of the book, I'm going into detail about how to kind of poke, kick the tires of all those bits, and how to look under what's going on when you run a container and how these things are actually being used. In this session, I'm just going to try to show you enough to just kind of poke your interest and get you started, and hopefully get you to buy the book. Okay, so that's a diagram. Let's now show you around a little bit of the VM. So if you download and import the VM from GitHub, this is what it's going to look like. So inside of your home, there's going to be a folder called source. Inside of that source, I'm basically checking out all the source code that comes with the book, as well as the examples. And inside of the examples, you are going to see different chapters of different folders for different chapters, and in particular the one that we'll be looking at today is the poking Docker one. You'll see that I've prepared 5 experiments. Hopefully we'll have time to go through all 5 of them. I'm not sure if we're going to go on different tangents quite yet. I'm hoping to kind of see how this goes. But the plan is to show you like the basic chaos experiments that you might be wanting to do. Okay, so going back to, I'm kind of making the assumption here that if you are watching this video, then you have some kind of interest in what chaos engineering is. But if you are new to that, let me just quickly switch the browser. This is what I basically consider the canonical definition of what chaos engineering is right now. If you go to www.principlesofchaos.org, This is the definition. So basically, the chaos engineering is the discipline of experimenting on a system in order to build confidence in the system's capability to withstand turbulent conditions in production. Note that if you just Googling that chaos engineering, one of the first things that you're going to see are breaking things on purpose or breaking things in production. But what chaos engineering really is just this experimentation on a system, and it can be big system, it can be complex system, or it can be as simple as a single process on a host. And by experimenting with it and seeing and confirming scientifically that your assumptions, what you think is going to happen, is actually happening when that situation is going on, that's where you create the value of chaos engineering. So what you typically do, kind of like the unit of chaos engineering, is a chaos experiment. And it is as simple as 4 steps. First, you look for a metric that can be reliably measured. Then you you measure the steady state. And if you are, well, let's say that, for example, we want to measure our application we think that our application is not going to be affected by some other event. Then we might pick a metric for observability that is, for example, a percentage of requests that are going through, successful requests. And that would be our observability metric that we can measure. Then the steady state would be that, yes, indeed, it's 100% okay. And then we introduce some kind of failure and we make a hypothesis, which is essentially a guesstimate of what we think is going to happen about the system. And then we run the experiment and we're either right or wrong, and we validate or we falsify our hypothesis. Okay, so let's go back to our VM. If you have used Docker before, you're going to be familiar with that, but I just wanted to kind of give you a quick overview first. So let's say that what happens when you run a container. These are the images that I currently have downloaded on my VM. This comes pre-configured. What happens when I do a Docker run, and let's say that I would like to use the option RM to delete the container when I'm done with it, TI for interactive access, and let's say that I want to run my Ubuntu focal. What happens when you start this container is that we have a brand new process, and all of the things that we saw applied before are working to kind of trick the process inside the container into thinking that it is an isolated machine, right? So for example, if I just look at my processes, you'll see that the bash that I'm running inside of this particular container thinks that I have a PID of 1. And the PS is PID of 8. Meanwhile, if I did the same thing from inside of my process here, I am already at PIDs in the 14,000s, showing that, from just an observation like this, we see that there's already this isolation in terms of processes, the PIDs that we can see going on. So that is what I, if you're just starting with Docker and the chaos engineering, that's probably like one of the first things that you would like to check, right? Whether the PIDs or whether the things that are happening inside of the container can be affected by things running inside of other containers, or potentially running on the host itself, right? So let's start with this as an idea for a first chaos experiment. Let's say that we wanted to check whether a process, for example, that I'm running on my host here can be killed from inside the container. So in order to do that, the VM here comes with, instead of experiment 2, a very simple script PID printer. As you can see, it's basically doing nothing. It's printing the date, then it's printing the PID, and then it's sleeping for 2 seconds. So this is done so that you can basically see easily the PID of the process, and you can see that it's still running because it's printing things every 2 seconds, right? So if I wanted to now design a chaos experiment around that, probably one of the simplest chaos experiments that you can come up with, just to warm you up, it would be, okay, so my observability here is that I can see the process running, I can see its PID, and the steady state is that it is running, nothing bad is happening to it. And then my hypothesis would be, just an educated guess, that I know that containers are supposed to be isolated processes, so I shouldn't be able to just call this PID from inside of the container and kill it. And to implement that, we would do exactly that. We would take this PID, copy it, and go and try to kill it. So if I just open another tab now, and I start a container, so let's say that I'm going to do docker run. Again, I want to delete the container when I'm done with it. I want it to be interactive, and I want to run my Ubuntu Focal. I'm now inside of my container. I can see it here that my bash has a PID of 1. Now, if I copy this 14380 process from here and from inside of the container, I'm going to try to kill it with just kill. I'm going to see, whoa, there is no such process, right? So that means that my hypothesis was right. That means that I was indeed in some kind of separated, isolated thing. And if we go back to the diagram of the technologies that were involved in Docker, this is what the namespaces are able to do for us. And just so that you are able to design meaningful chaos experiments, let's go and snoop around a little bit and see how the namespaces are working. So now I'm going to stop the, back to the VM. I'm going to stop my little sleeper situation here. Just going to kill it. And actually I'm going to kill this process too. And if you're new to the namespaces, man is your friend. You're going to see quite a lot of information here. This is man 7 of namespaces, but this is a good starting point. You don't really need to leave the terminal to get to know quite a lot about that. For example, the proc/proc/PID namespace directory that we'll be looking into in a minute. But if you're completely new to namespaces, probably the first thing that you want to do is run ls/ns, basically list namespaces. And if you run it as a user, this is what you're going to see. If you do run it with sudo, you're going to see slightly more of these things. But you can already kind of get an idea. You have the namespace number here, then you have the type, and here you can see the different types. There's a month, there's a net, there's IPC, UTS, user, PID, and cgroup, right? And then you can see the number of processes in it, the first PID in that namespace, the user who owns it, and I think this is the first command corresponding to that PID. And if we just take a look at how many of these are there, we're starting with 18 namespaces by default. Okay. Now, if I go to the different tab, to the second tab, and we do the same thing again. We just start a random container that's not really doing anything apart from running a bash session. And we rerun this command here. We see that we have 5 new namespaces, right? So if I just drop the WC, you are going to see here where is our new stuff. This is the bin bash. So we see that our process 14,811 here has new namespaces. One for NAND, one for UTS, one for IPC, one for PAD, one for NAT. And if I go ahead and kill this one, this process here, and count them again, boom, I'm back to the 18. So this already, if you know nothing about namespaces, is already showing you that the Docker is creating this new structure for them. Right? So let's take a look at this process here. Right? If you do ps of 14,987, you can see that this is our bash command, right? What else can we do? If we go back to our man namespaces, you can see, well, we have the description. A namespace wraps a global system resource in an abstraction, makes it appear to the process within a namespace that they have their own isolated instance of the global resource. And this is basically all that you need to know about namespaces in our context. There are the different types: the C group, the IPC, network, mount, PID, user ETS, and all of them behave a little differently because they wrap different resources, but the idea is the same. It's to kind of trick your process into thinking that the resource that it's using, it's for them only. The thing that I mentioned before, this is kind of interesting, you probably should know that, is that you can get a lot of information about the namespaces that you get for the process just by using the sudo file system in /proc /namespace. So this is giving you an example of, for example, checking the namespaces of the current process, and you can see that. Instead of doing that, let's see the namespaces of our container process. So we found here kind of manually looked for this particular PID. So if we just copy that and then we do ln ls of proc / our PID /namespaces with sudo, we're going to get a list of these links. Right, and notice that these are symbolic links, and they are kind of funny because if you try to just kind of follow them, for example, if I try to do C group here, if I try to ever go there, interesting. If I try to for example, read link on that. This follows this interesting format that this is the type of the namespace, and then within this brackets you get the actual namespace of it, the namespace number of it. Okay, so this is just giving you like kind of a vague idea that Docker is doing something and telling the kernel to create some kind of isolated namespace that is tricking the process into thinking that it has a completely different PID tree to what it actually is happening on the host itself. Yeah. So if we wanted to dig a little bit deeper into that, within the book, I'm going to more details and trying to kind of explain how all of this fits together, and giving you resources to learn more about what's going on in there. There's also, if you're interested, I am providing you with a kind of, if you go and take a look at containerish too, I'm showing you how to use and share to run a process within a particular namespace without using Docker. So if you remember, maybe you noticed that when the man namespaces, it's also mentioning here the API to use the namespaces. And the particular three things that are of interest are the clone, the set namespace, setNS, and unshare. And unshare allows you to basically start a new process within a particular namespace. And if we have time, we're going to go back to that, and we're going to try to see how we could achieve a result that is similar to what Docker is setting up using these little scripts here. But before we go to that, I wanted to show you some more chaos engineering. Because our first experiment was really quick. It was a success, I guess. You can say that the hypothesis was true, so our expectations were met. So another thing that you might be thinking about of doing, of verifying if you're just starting with Docker, is in terms of basics, you might be wondering, what kind of isolation I'm getting if I'm using containers in terms of storage. For example, you might be wondering if I run a misbehaving process from inside of the container, does it mean that it somehow protects me, isolates me from the possibility of filling up the disk, right? So if we wanted to do that, our observability would be to just, for example, check the usage of the system, right? So if we do just df, for example, we're going to see the percentage of the disk being used. Currently, my main drive is 30% used, and we could use that as a reliable metric of whether a process can eat up all of that. And then the steady state would be to measure the current usage. So you can see here that I'm at 30%, I have about 70% of the disk free. And then the hypothesis would be, if we're just starting with Docker, my expectation would be that there's probably some kind of default that Docker runs these processes with that is going to prevent it from using all of my disk, right? So how would we go about verifying something like this? Well, we would design a little experiment in which we could start a container, and we could try to fill up the disk and see if this is actually possible. All right. So I've prepared an experiment like this for you. So inside of experiment 1 here, there are 2 containers. One of them is control. And you can see that this is a very simple Docker file that's taking Ubuntu focal from a particular day as a base image. Then it copies the run script and starts it when you start the container. And what's inside of the run script? Again, it's a very simple script that does a loop. And actually, we put that in the frame so that we have at least some coloring. So we have a couple of variables. We have the file size and file name, and then we have a while loop that never ends, in which we try to use fallocate to allocate a file of a certain size. And then either we manage, in which case we just say, okay, go to the file, and we move on, or if we couldn't, we just print a message that we couldn't, we sleep for 2 seconds, and then we try to delete the file, and if we fail, we say that we couldn't, right? So we can actually run that directly on the host, and the output is like this. It's writing file, printing the 50 meg file, ls, and then every 2 seconds it's erasing that, and it's trying again. If you're not familiar with allocate, it's just a simple tool that literally allocates the space for a file. Okie dokie. So this is our thingy. So let's say that we would like to build this. I think I have a make file here. Yeah, so let's say that we're gonna build this into a container. It should be reasonably quick. It's not doing much. And we've built it as experiment 1 dash control. So inside of my images, I have a new image that I just prebuilt, experiment 1 dash control, and with the tag latest. Okay, and I can run it. If I do make run, it starts Docker, calls my container experiment 1 control, dash control, no particular surprises here. And it runs, tries to allocate the file every 2 seconds. Okay, now from inside of the other tab on my terminal, again, I'm gonna check that I have the 30% of my disk available. But if we go to experiment 1, and this time let's go to the failure, we have a similar situation here. We have a Docker file, again, super simple, that runs a simple consume script, copies it, and does nothing else. So from inside of the consume.sh, we have a slightly different situation here, that instead of deleting the file, we're basically allocating the file, and we stick, and if we allocated it successfully, we just move on and we try to write more. And if we failed to write the file, we sleep it for 5 seconds and we just keep restarting. So we're going to basically try to fill in the disk by doing that in chunks of 50 megs. The 50 megs chunks are primarily because it's going to go quickly. B, that should leave enough when we actually do reach the limit. It should leave enough for the system to not go funny as a whole. So once again, I believe I have a little make file here that I can use. So it would just do make build. We're going to pre-build the other Docker image. Docker images. Now I have the experiment control, and I also have the experiment failure. And I also have the make run. But before I do that, I'm going to enter, start yet another terminal window in which I'm just going to watch on df. So that we can see what's going on. Okay, so everything's set up for our experiment. We have the visibility, the observability, which is the amount of disk used, and the process, the control process that can write and doesn't complain. We have our failure that we introduce into the system, our process that's going to try to use up all of the space. And our hypothesis was that surely Docker must be doing something intelligent here, and it can't just run things and let them use all the space, right? So let's see, let's just run down the experiment starts writing the files. We can see them here. If I switch to the other tab, I can see that we're already at 100% of my 32 gig disk. So things are not looking very good. My writing process is starting to fail because it can't, there's no space left on the device. And let's see how my control is doing. Well, this one also can't, no space left on the device. So what does that mean? That means that despite the fact that we're running this application in Docker, it was actually able to fill up all of the disk, 100% of our usage. Does it mean that it was contained? Well, that's a good question. I guess it depends on the definition of containing for you. It definitely means that if you run it the way that I just ran it, with just Docker run, low disk space, I'm just going to ignore that, you are not immune to running out of disk. So what we're going to do is that I'm going to kill now the offending process here because of the fact that I had the --rm flag. All of the files that were written by that process are going to be deleted on deletion of the container. As you can see here, my control process has already picked up and is continuing to write its files like if nothing happened. And if we go back to our DF, you can see that we're back up 30%. Okay, so we can see that with a few lines of bash, I guess around 10 lines of bash in total, we're able to run a simulation that shows to us that our guesstimation, educated guess of what to expect from Docker storage solution, they were not correct. Now, to be fair to Docker, there are some options that you can use, and even here inside my makefile, I have a command line that could let you use the storage option to limit the size of the size of storage that the container can use. The problem here is that if I do try to run that, the storage option is supported only for overlay if you are using the XFS file system with the pquota mount option, which my VM here isn't. And so if you wanted to be able to do that, you have to know that this option exists and need to be able to need to set it. Right? So hopefully what this illustrates to you is that with the approach of chaos engineering, we can employ very simple methods to check properties of a system that we believe to be true, and then actually go about that scientifically and verify that our assumptions were correct and that what we thought was going to happen is actually happening. All right? So this covers the disk space. Probably the next thing that you're going to wonder is, okay, so how do we fare with other resources like CPU and RAM? Okay, so this is obviously a valid thing to think about, and I've prepared another experiment to illustrate to you how you can do something like that. So inside of experiment 3, if you're following up with the same VM, I've prepared a little, very simple Docker file that basically starts with a vanilla Ubuntu and then installs a command called stress. So once again, I prepare the make file. I have to just do make build. to build a command, to build a container image that has the stress command in it, and we call it stressful. So you can see it's being installed, and I have a new image called stressful. So now I can run that. TI stressful, and I'm back in a bash session, except that now I have a new command here that allows me to to run bench tests, basically. So the stress commands allows you to do things like eat up CPU, do things like eat up disk I/O or block device I/O, and do things like allocate memory and do it continuously to see what happens with your system when you try to do that. Okay, so what should we start with? Let's say that we would like to verify that Docker, if I start a container with Docker and I say that I would like it to only be allowed to use half a CPU, that indeed that limit is going to be enforced. Okay, so how do we verify things like that? Probably the easiest way to do that would be with something like npstat. And let's say that we want to refresh all CPU usage every 2 seconds, maybe 5 seconds, a bit. So a little bit less aggressive. So if you're not familiar with the output of the npstat, it has a lot of different options, but this is presenting you with the all, which is like the overall usage. I have configured my VM to have 2 virtual CPUs, and then they're numbered 0 and 1, and you can see which CPU is being used, how much, and what percentage of time is being spent in different categories. So right now, my system is basically idle. My VM is at 96.5% idle, and both of the CPUs are doing essentially nothing. There is a few percent that is spent in the user space, a very small percentage in system space, and basically no time spent anywhere else. So the npstat is going to show us what is the real CPU utilization, and with the all option we can see which how many cores are actually getting to work. So with our stressful image, kind of experiment that we could conceive would be, for example, to say we will start our stressful container with a hard limit of half a CPU, and then we're going to try to run stress test inside of it to use as much CPU as we can and see how much as much as we can it actually is in practice. Okay, so let's try that. Let's say that we want to, let's start a new container. Let's say that we're going to give it CPU equals 0.5 to give it half a core. We're going to make it interactive again. I'm going to delete it after when I'm done. I'm also going to actually name it experiment 3 now, so that we can find it more easily later on. And I'm running the stressful command, the stressful image. CPUs, and boom, I'm inside of a container, and in theory I should be limited to the half CPU. So my hypothesis at this stage I'm going to try to not be affected by our previous failed one. So let's assume that, for something like the CPU, Docker should do fine, and it should indeed let us use only the half CPU. So now, to implement that, I'm going to use the npstat as the visibility tool in one tab, and the other tab I'm going to run the stress command to try to use as much of the CPU as I can. So again, if you run stress, you see that stress accepts the C or CPU flag in which you can give it n workers spinning on squirt. So basically, if we have two CPUs on this machine and we try to run two workers, my hope would be that this would use both of the vCPUs if the Docker doesn't work, or on the half CPU in total that we gave it. We're also going to give it timeout. Actually, let's just start with that. So if we start with stress CPU 2, it's dispatching two CPU hogs. Let's see what happens inside of the npstat. So you can see that instead of 96% idle, we're about 65% idle. And you can see that both of our cores are used about 29–30%. So this is a little bit more than so because of the fact that we used two CPU workers, the load is a little bit spread. So maybe before we do that, I'm just going to go back and just do a single CPU worker so that it runs on a single CPU. So it's easier to see and compare. So this is the let me run this more often because the 2 seconds feels like forever. Yeah, so you can see that one of the CPUs is being used roughly 50%. And that the other one is kind of jumping all over the place, but this is slightly more than the half CPU that we expected to see. Well, mainly because apart from Docker, there are other things running in there. But the other CPU is basically, I think it's not stopping. But overall, from our two CPUs, we seem to be using roughly a quarter of it, which is half a CPU. So it seems to be working reasonably well. To confirm that, we could start the container now with a different value. If we give it a CPU, one CPU, for example, and try to start it like that, and we run again stressed with a CPU, and let's just say that we run one worker that should be spinning as quickly as possible. You can see it's a little bit better that one of the CPUs is working crazy, basically being at full utilization pretty much all the time, and the other one is just busy doing other stuff inside of it. And if you're still feeling a little bit unsure about that, you can also give it a small percentage. But we need to remember that there's other things happening in the system. So the 10% of the CPU that might actually be slightly easier, harder to spot. Yeah, I see that one of the CPUs is slightly busier than the other one, but it's kind of harder to spot it with a small value like that. Okay, so it looks like the CPU is being contained. I guess what we should check is also, if we give it two CPUs, whether it's allowed to use two of them as a control group. And we can do that by just doing 2 workers. That should be able to use up to 2 CPUs, so we can see clearly that right now it is actually able to use that. So Docker is doing a good job. It's implementing what we're asking it to. And if you recall from the beginning of this stream, it's kind of interesting, especially the first time I'm doing it. So I'm still getting the hang of it. This is what the C groups are responsible for. So the C groups are allowing you to set limits for particular containers, for particular processes that limit things like CPU and things like RAM. And if you're curious about how to kind of look under the hood and see how all of that is configured, you can, well, I'm referring to the book in which we go into the details and we see how to sneak peek into what's going on. Okay, so CPU is good, which makes me think, okay, we should be checking things like RAM now. I'm wondering what's going on if you try to use more memory than you're actually being allowed. So if you are familiar with the OM-kill, then you'll know that we should be, I don't actually have anything in there, but that's fine. We'll see it in a minute. OM is a mechanism in Linux that in desperate times where there is not enough memory available, can pick a victim and kill them and sacrifice them on the altar of stability of the entire system. And as you'll be able to see in a minute, sorry, the same mechanism kicks in when you start a process that should be limited to a certain amount of RAM, and that process is using more. Okay, so let's try to do another experiment now. It went well with the CPUs, so let's make a hypothesis that if we start a process that's only given a certain amount of RAM, let's say that we give it 128 megabytes of RAM, and we try to use more than that, then Docker should, the process shouldn't be allowed, and well, the educated guess would be that the process will be killed if it ever tries to do more than that. So starting a container with, let's go to experiment form. Starting a container with memory limit is with Docker is as simple as it was with the CPU. We just run docker run with -- memory, and we specify 28 megs. So inside of this container now, we should be limited to that. Okay. So how should we go about observing observing the usage? Probably the easiest thing to do would be just to run the command tab, in which we can see the memory being used. We can actually cycle through the different visualizations. If you press M, this is the numerical values. This is a bar, more pretty bar, or it can disappear. So just to visualize it here, because the numbers might not be that important, this is what we're currently being used. Okay, so from inside of our container, from the stressful image, we're going to use again the command stress. Like I mentioned before, it allows you to run with -n for memory with a number of workers allocating a certain amount of memory. So let's say that I would like to run the stress command with a single worker that allocates the memory, and I would like it to use the VM bytes. I would like it to use, let's say, 512 megabytes. So what would be the hypothesis? The hypothesis here would be that I can't really run that my process is going to be killed, right? My observability here is that I'm going to see whether the process is killed or not from inside of my terminal window, and also in the top command I'm going to be able to see how much of the memory is being used. Or if you're not comfortable with top, that is kind of busy, the other thing you can do is you can use free command, or you can watch it if you wanted to. So right now I have 2.3 gigs out of 3.9 available, and let's say that I want to watch it. Okay, so the observability is there, the steady state, we just saw it here, 2.3 gigs available, and my hypothesis is that I shouldn't be able to run that, my process should be killed. So let's see what actually happens. So this is a little bit suspicious because I'm running my stress test and it's claiming to be using that. My available memory went slightly down, but my process is definitely not being killed. If we kill this and we go back to the top, I should be able to see my stress command. You can see it as the top value actually. It's claiming to be using the 500 megs of virtual memory that we're using and that we asked it to use, which is more than we gave to the actual container that we started with, and Linux seems to be completely fine with that. Both Docker and Linux are not doing anything to prevent that, so it's a little bit weird, right? Yeah, it's running happily and nothing seems to be happening. Okay, so let's see what the system is telling us about the memory usage of that. Inside of the /sys pseudo file system, you can actually see what the memory usage in bytes as reported by the system are from the perspective of C groups. So if you wanted to do that, we're just going to need the container ID because of how the things are set up inside of the C groups. Again, if you'd like some details about how to look under the hood of that, they're in the book. But right now I'm just going to quickly show you how to get that. So let's start by getting the container ID. And the container ID, we can do that by running docker inspect. Docker inspect of the field. And this is a little bit verbose, but this is how you can get a specific field out of Docker. And we call that experiment 4. Experiment 4. So I have my CID, and with that CID, I can now go and search things. And the cgroups version that I'm going to show you, it's still version 1. But well, it's just kind of FYI, the second version is still not widely adopted. But if you want to just take a quick look, what you need to do is you need to go to sys/fs/cgroup, and then inside of that we are going to look at the memory subsystem, and inside of that Docker creates its own subgroup. And inside of that, actually I only have a single container, so I didn't really need to get the CAD, but I have it anyway. And then inside of that, there is the memory usage in bytes that we're interested in. Is it usage? Is it possible to type on vision like that? Okay, let's just go there. Memory usage in bytes. Usage. Sorry, that was a little bit funny. So this is the number of bytes that we're seeing that are being used by the application, and we initially gave it 128 megs. So let's just do a quick calculus. 128 megs in bytes. Okay, let's do it the other way around. I don't want to put it down like this value. Let me just copy this value and let's see what this many bytes that corresponds to. That corresponds to 134 megabytes. So this is pretty confusing. Well, this is just over the amount that we asked to limit our container to in terms of the limits. The container is still running when it's trying to allocate 512 megabytes, and nothing is happening. So our hypothesis was wrong about what's going on there. And what's actually going on is that the system is just a little bit smarter than we thought it would be, and because of the fact that the stress command doesn't actually do anything with that memory, it's going to give it to it, and then it would only fail if it tried to do something. So just to confirm to do that, one thing that I always want to do is to do like a fork bump. So if we try to just do that instead, the quickest and easiest fork bomb in Bash is probably going to be just a function like this that calls itself. Let's try to see what's going on. Okay, too many open files, cannot allocate memory. Okay, so this is finally looking like what we're expecting to see. I hope that I didn't kill my VM by doing that. Come on, okay. Yeah, okay, it's being a little bit slow. Let's see what top says. What did my this is dying? So I mentioned before that you could look in the message for the messages, and let's see if anything is showing up there. It's not. Yeah, so it looks like my process fork cannot allocate memory, which is good because that's the kind of situation that we're trying to create by limiting them. But I'm just wondering how I'm going to get it done. Probably just going to do docker ps and docker force to get that. Okay, so it looks like running fork bomb did run into our memory allocation problem, which basically brings us to the conclusion that although the initial experiment was faulty with the stress command, where the system was just a little bit smarter than we expected, we do get to experience the process running out of memory if we try to use more than that. If you're curious as to how to actually look into what's going on when you run a process with memory limit like this, you can do that by, let's go back to the sysfs cgroup memory subfile system. So if we go to the only folder is here, this is the container ID, docker yes. You can see that the container ID starts with the value here. And then inside of here, you have plenty of information that's stored in this different files. So for example, the soft limit in bytes, the limit in bytes. This file should give us the 128 megs, which is interesting. So this is again this value, which should be the 128 meg that we gave it. And just confirming. Okay, this is supposed to make the points. Yeah. Okay, so this divided by 1.4. Yes, so sorry about my mental notes. This is this is the 128. Oh, sorry, you couldn't actually see that the whole time. So if I just take this value and divide it by, this is into kilobytes, and this is into megabytes, I get the 128 megabytes that I was after. Oops, and I accidentally closed my tab. Sysfs groups memory docker sorry, I also accidentally closed my docker container. So as you can actually see here that Docker is creating a new folder for the container with the same ID. If I just go there, yeah, so this is the limit in bytes that's being set on my process, and there's various other things that you can set for this particular container. If I close the container now, and instead of just running it with the limit of CPU of memory, I also add the CPUs. Let's say that, for example, I wanted to add half a CPU limit. and I go back. I have the new container ID. Actually, sorry. Let's go to the CPU. And inside here again we have the Docker name, and then we go inside of the container. We have the various things that you can see about the CPU. And CPU is actually a command name for the CPU limits and the CPU accountant. So you can see them here. One of the interesting things that the C groups CPU limitations allow you to do are that you have basically two ways of setting them. One is the CPU shares, and if we just take a look at this, you're going to see that it has a value of 1024. And the CPU shares is kind of like a soft limit. It only kicks in when there are processes that require more CPU, that there's CPU available. And the shares are basically like weights for the processes. So let's say if you had two processes that both had 1024 CPU shares and they were competing for CPU, in that case the CPU would schedule roughly half of the CPU time for each of them. But if you had one of them that was at 1024 and the other one at half that value, for example, you would end up with a proportion of the shares of the CPU time that are in the same ratio that the shares are. So you can actually do that in Docker too, but that's not a hard limit. And when you run with the CPU, that's where Docker is setting hard limit. And the hard limit is implemented in two numbers. So one of them is the period microseconds. So this is the accounting time. So for the 100,000 microseconds, every 100,000 microseconds, the operating system is going to try to limit, well, it's not going to try, it's going to limit the amount of time that can be spent executing this particular process. So you can see that the half CPU that we run with in Docker here, and the CPU is equal 0.5, that translated into the value of 50,000 for the quota microseconds, and the 100,000 period, meaning that basically half of the time can be spent there. So this is worth remembering that this is not just a single value that's being set there. This is, well, basically the amount of the size of the period that you use can have effect on how choppy or how smooth the amount of CPU that your processes are going to get is going to be. Alright, and if you're just curious, and you don't believe me, if you set it to, for example, 1.5, let's say that I want my process to be given this much. I'm going to go back here into the new container ID. A folder created by Docker because I restarted the container. If I do cut of the quota, now it's 150,000, and the period is still the default value that Docker starts with, which is the 100,000. You can see that I allocated more microseconds than the size of the period, meaning that I can use more than one CPU to do that. Okay. So this is pretty good. Once again, just kind of trying to pique your interest and hopefully I'm succeeding at that, and to kind of show you that the Docker, the Mystified is not as scary as it might look initially. it actually leverages a lot of existing stuff, and all the existing stuff comes with documentation and can be understood. Okay, so I think we have about half an hour left. So in that case, I wanted to do two more things with you. First, I wanted to show you how we can kind of implement a little bit of the Docker using the existing underlying technologies. Kind of show you that it's not really that complicated, because most of the heavy lifting is actually done by Linux, and that can actually be fun to understand, the underlying thing. And then after that, we'll do one more experiment, but on a slightly different type. We're going to actually deploy an application, and then we're going to see what happens to it if you affect the networking. And we'll see how fun that's going to be. So the first thing I wanted to, let's go back to, for a minute, to the browser and back to the underlying technologies. So I would like to first focus your attention for a minute on chroot and the file systems. Docker is using the UnionFS, which is copy and write, which is kind of cool. But I'm not going to go into that right now. I'm just going to focus on what chroot is actually doing. Okay, so actually, if you want to see what chroot Cisco is doing, Mon2 chroot is just one call away. It tells you exactly what it does. It changes the root directory of the current process to that specified in path. The directory will be used for path names beginning with /, meaning that basically you can tell the system that this process should now be kind of locked into a particular subdirectory, and it won't be able to go anywhere above that. So in order to accomplish that, I've got a little script for you that's called a new file system. And again, it's just a few lines of bash. Sorry. Just a few lines of bash. And what it's doing, it's kind of described here anyway, but it's we're going to start it with some name for the new file system. And what it's going to do is it's going to go through the tools variable here, in which I specify the binaries that I want to copy to my new sub file system. In particular, just doing a very minimum here that is going to let us run some examples. I'm taking bash, ls, working directory, copying vim, and a bunch of basic utilities so that we can actually do something inside of that chroot, because otherwise we would be stuck. And then I'm copying them to a subfolder that we created in step 1. And step 3 is a little bit more tricky, because in order for the binaries to actually run, we need to copy over the shared libraries that they rely on. That's why I'm using the LDD for. For each of these tools, I'm just grabbing for things that are starting with either userlib or lib, and then I'm copying it over to the names to the dependencies. And then I'm copying over the actual dependencies by first making them unique and sorting them to the new file system root. And then just a little message in bashrc so that we know that you are inside of the new container if we ever get to actually start with it. And that's it. So if you just run the script and just pass the name of the new file system, so let's say you want to do it on Twitch. And obviously I can't spell Twitch, but let's fix that. That's embarrassing. Twitch. you can see that it does what we just described. It created a new folder. It copied bash, ls, mkdir, ps, and a bunch of other things. And it created this new subsystem. So if we do tree, okay, on that new file system, let me just install it real quick. Tree of my Twitch folder, I'm going to see what we actually copied over. So it's as basic as it gets. Inside I have my bin directory with the executable files that we decided to copy over. I have a home with chaos for the chaos user, and then I have the libraries that we copied over because the binaries we wanted were dependent on it. We have some lib64 too, and then the touch and thing happen to be in user bin, so we copied them over too, and some user lib stuff. Okay, so now the next step to do that, to actually make use of that, is the chroot. If you type that with help, it's going to tell you how to use that. So it's really not rocket science. It's chroot with the new root and a couple of arguments. I've prepared another script for you. Containerish, containerish. That actually, that's already, sorry, that's the second part. We'll get to that in a second, and that's with the unshare. So if we run chroot with our new folder here, and we need sudo access for that, boom, look at that, we are inside of welcome to the new kind of container. So where are we? Well, ls, we have the bin home lib. If we try to go inside of the bin, that looks fine, but if we go back and we try to go back again, nothing's happening, but it's because this is actually our new root of the file system. So inside of the bin we have a few things. So for example, I can touch a new file, I could vim new file, I can say something, hello twit, hello, what did just happen? Hello, it's just a cast tab. Hello, and if we close that, do we have cut? So if we do cut my new file, it's working just fine, right? The PS, on the other hand, is not going to work unless we actually mount the /perk inside of that, because as you can see here, there's no such thing as /perk. But we'll just let you know. So let's exit that and let's rerun our tree again to see what changed. And you're going to see that inside of the file system, at the root we have the new file, and it's just a file like any other one. Twitch new file. The only difference really, the chroot, is that from the perspective of that particular process, there's nothing else, right? It's this particular point, this particular subfolder that is visible to you, right? And this is another figure from the book, which illustrates that inside of my host file system, if I have this fake root dir and then I start with the fake root dir as my ch root, the contents of that become everything that my new application is actually going to see. And this is what ch root works like. Okay, now back to the VM. So this is kind of approaching a little bit what Docker is doing for us. I mean, Docker manages the entire contents of the container. It manages the images. It manages pushing them too. I didn't actually mention it before, but the kind of entire value that the Docker containers add on top of all of this, because you might be wondering, okay, so if all of these technologies have been and are in the kernel, why do we need Docker? Well, Docker just makes all of it easy, right? So Docker gives you things like the format for Docker file that you can later use to run Docker build. That's going to produce an image. It also gives you an API for the Docker registries where you can push the images so that other people can download them. And then, like in this schema here, in this illustration here, if I do Docker build and create the image A, then I do Docker push to some kind of registry, someone else can do Docker pull and get the same image, the same layers, and then Docker run it to start the container. So despite the fact that all the heavy lifting is done by the Linux kernel, Docker made it awfully easy to basically use it as kind of ultimate packaging tool. Many people complain about container security, but that's not really the biggest advantage of using Docker. The biggest advantage is that you can package the applications, at least in my opinion. You can package these applications and you can send them into the world, and they're going to have the exact same contents and the setup of the VM. Okay. So we covered the ch root and we created some kind of very, very basic file system. What would be the next thing that we would need to do to make it behave a little bit more like Docker? Well, we could add namespaces. So going back to our VM, I think I mentioned before, here we have the next step in containerish sh. Let's just display that better for you. So what this does is that it leverages our new file system script to copy over some binaries and prepare it. And then it adds another step. It creates a new PID namespace and starts the ch-rooted bash session from inside of that. It also does as you can see here, it also creates a /proc folder, and then it mounts processes to /proc so that we can use them with PS and make that work, and then it executes a bash session. Okay, so this is all done with the unshare command. That you can see the docs for, and it's pretty straightforward really. You run unshare with some options, you specify the program arguments, and it defaults to bin sh. Right, so let's see what happened. So we had our Twitch thingy. Let's say that did we specify here? Yeah, so let's say that we're going to run it with containerish sh, and let's say that we're just going to call it very dully Twitch2. And boom, look, we're inside the container. Let's see what's going on here. We get again the same dull, very simple file system. But the nice thing is that we can actually do a PS now. And just like we saw in the Docker before, we can see that the bash process from the perspective of the container-ish is actually showing us PID1. We go back to LSMS with sudo, and we count it again. You can see that we have the 19 lines, meaning that we have the extra one. And you can actually see it here. It's not that difficult to spot. This is the PID a namespace that we just created for what we wanted to do. So this is still not a real container, but it's getting a bit closer. We only created a single type of namespace. We created a PID namespace. All the other namespaces are still shared here. So, for example, if we take this PID and we take a look at ls sudo ls /proc namespaces ls close. You can see that this PID number here corresponds to the PID namespace, the 2173. But you can see that all the other ones, for example, the mount namespace, the default one that's shared across all the processes, is still the same one for our process there. Okay. So this is pretty simple stuff so far. Probably the next thing that you would like to do, and you're wondering, okay, so is it possible to maybe go into that namespace and just execute something to an existing one? And the answer is obviously yes. And you can do that with ls-enter. Run a program with namespace of other processes. And in order to do that, one of the simple ways would be to just use the -t for target, in which case it's just going to go and attach itself to the PID, all the namespaces that particular PID corresponds to. But because of the fact that we're just dealing with a single PID namespace, it might be more interesting to do it kind of manually. So if you wanted to do to just attach yourself to the PID namespace of that particular process, you can just specify PID equals, and here we specify the actually copy PowerPoint, and now the PID number and the PID link, and all of a sudden now you can see the other ones from that particular namespace. Okay. Did it work? Yeah. Processing. Yes. Oh, that's sorry for the okay, let me see what I'm doing here. So let's go back and see if I just picked the wrong one. This seems to be the one. Maybe. Okay. Okay, let me try to do it differently. Another way that you can do that is you can just specify PID, you can specify the target. And I'm still not getting inside of the right namespace. Okay, let me see. Sorry, this is running from the VM, it's running a little bit hot right now. I do have the backup script in case this happens. But I thought I would be able to just do it now. Yeah, yes, enter PID target containing PID. That should have worked. What's going on So, sorry about that. I'll share for PID search root. Okay, so it should have worked. English. Start again. Okay, so I have my sleep. I don't have sleep. Okay. Inside here, I got a PID here, and I'm just wanting to attach to that particular namespace. So I should be able to do just sudo ls enter the PID namespace and target. This is a PID and just run developing dash direction and the PS. Still not doing what I wanted to do. Okay, let's do it differently. So if I take PID namespaces and all the things PID namespace, and I'll just grab file as PID. Yeah, there's the big bash on the side of the target. So just a second. Okay, so let me just, I'm not sure right now, I'm not going to try to debug it on Vision. Let me try to instead do the, I started through Docker. If I just put this one like a random container and then test, and I just do the Ubuntu. I'm gonna remove this. I just want to start a flying container that's going to have its own PID. And then inside of here, I'm just gonna do I'm just going to do this, and let's say that I'm just going to start a sleep so that it sleeps for a while so that I can find it. And let's get out of here. So I did it again. And now I have this backup script here, and then I'm just gonna quickly load it actually. Let me just let me quickly modify that. And I'm just gonna this to test. And I'm going to attach myself a particular space and doing the PID. And now instead of sleeping here, if I do ps-a, I can see the container, the process that I started here by attaching myself with /enter inside of that. I'm not too sure what I messed up with my manual container, but I just wanted to show you that it's actually pretty easy to attach yourself to an existing one. Okay, so okay, so let's go back to our kind of cook at home container. One last thing that I wanted to show you about that is that new containers to addition is that on top of doing that, we are also going to add some cgroups limits. So let me do that containers too. So I wanted to kind of show you just that it's kind of easy to do it yourself if you know how it's set up. This is leveraging the previous new file system script. It's also doing the exact same on share with PID and chroot. The only difference with the previous step that we did is this step A and B, in which we are generating a random UID, and then we are preparing the file system on the CPU and memory in the cgroups pseudo file system. And put in the values that we want. So for example, we put in the RAM limit, which here looks like it's defaulting to, what is it, 5 megs or something. A CPU limit, and that's defaulting to 50,000 out of the, once again, if you remember, the default that Docker was setting was 100,000 for the period microseconds, and then half a CPU corresponds to half of that value, so 50,000. So we're basically replicating that. So we're putting these values inside of the /sys cgroup CPU in a subfolder. And then we're basically just running the new file system. Then we're putting, and this is where we kind of link the cgroup to the current running process. basically by doing this, we put the PID of the current bash process and we send it to sys fs cgroup CPU and memory UID tasks. And by adding that, we basically link the PID to the namespace, to the cgroup that we want it to contain. And then we run the cd run share like we did to create a new PID space. We run the chroot from inside of that, and then we run bash again with mounting the /proc. So this is getting us a little bit closer to what we wanted to achieve. We go back to our diagram. We are handling the chroot, we're handling the namespaces, or at least one of the namespaces here to kind of show you with the PID how to use that, and the cgroups. The other ones we're not going to handle them today, but with this we're already getting a pretty good approximation very quickly for what we can do. So let's just run that. Containers -2, and let's just call it Twitch 3. So from inside of this, you can see once again that we have the PID namespace that's working well. And if we were to actually go something didn't actually work here, invalid argument for the quote. Let's see what happens. So this is the unique ID. So if we go to cd, so maybe I must get it pretty slow right now. I think my laptop is really overheating. DC groups and my name is that better? CPU. And then our table. And let's see what ended up being. Cut. So we have this value, that's correct. And this value is -1. So let's see what we messed up with the script. Let's kill this. What did we mess up here? So the CPU limit is supposed to be 50,000 loading points. Oh, right, sorry. So instead of passing Twitch 3, what I should have done is pass the first argument. Sorry, in the previous scripts, the first argument that I was passing was becoming the new file system, and here we're generating a UID, and the first argument is actually taking us the CPU limit. So I shouldn't have run it with Twitch 3, I should have just run it like this. Okay, so this seems to have worked, and let's just double check that it's getting the right values by going back, copy pasting this, and now CPU CFS quota is 50,000 and the period should be 100,000. Okay, showing that we did get indeed half CPU that we only set up. Okay, so with this, you can see that we are getting something that's kind of almost containerish, like by leveraging the cgroups to limit the memory, and leveraging the namespaces to limit what PID it can see, and also leveraging the chroot to actually implement a different file system. So I'm going to stop here. and I'm going to go and do one last experiment with you that is slightly different to what we did before, and we're going to look at some networking. So if I go back to my examples, open Docker, I have an example stack, an example application that we can start, and it's from the book. It's the newer stack. This is a description of two services. One is a DB. It's a MySQL 5.7 DB here, that you can see is completely misconfigured by specifying the root password to be not very safe. And then the other service is a Ghost. It's a blogging engine written in Node.js. And it's basically just getting the environment variables that set it up to use the MySQL database and root on the same localhost with not very safe password and the database. So if you wanted to run it, we can first need to docker swarm init. Then we can do docker stack deploy. Docker stack deploy, and we just give it the actual config, which is the newer stack, and we're just going to give it a name. It's called reality. Docker. Okay. So if we do docker stack ls, it's going to show us that we have a single mirror stack that has two services in it, and it's orchestrated by swarm. And if you do docker ps, we should be seeing both of these things coming up. And because they're not, something is okay. Nothing's working. Okay, well, this is live coding. I guess it just took a little while to actually download the images. So we can see the images coming up. You can actually go and maybe check one of those docker logs and see if it's happy. It goes for 20 seconds. Okay, so assuming that my VM doesn't go up, which might be a healthy assumption, I should be able to go to home, out port 8080. Yeah, and this is my ghost blogging platform. Okay, so if we just kind of kicking the tires of it, you might be wondering how quick this thing actually is. So if we just do a single curl with 1.0.31, port 8080, that works. So to get an idea of how quick it might be, we might want to run AB. So if you're not familiar with AB, it stands for Apache Bench, and it can generate traffic and generate statistics about how quick a website is. So if we do sorry, so AB is probably mean that I didn't put a slash at the end, and it generated a single request with concurrency level of 1. So let's do something more useful. Let's say that, for example, we're going to spend 10 seconds with concurrency of 1, and we're going to ignore the header, the different length of the request with /l. It's going to go ahead and it's going to spend 10 seconds generating load onto our website and checking how quick it is. So we're calling the website on localhost. Given the fact that it's just a little VM, it's not that quick, but we're getting about 113 milliseconds per request. So within the 10 seconds, managed to generate 88 requests. If we run it a few times, we should get similar numbers. But the bottom line is that this is, well, kind of like a starting point. Document is length is variable, we're hitting the right port, and it seems to be working. So with this kind of application, we have a server that connects to a database, and with that, from that database, it's going to get all the data that it's going to display. So very standard application, nothing particularly surprising here. So, it would be a shame if someone did some chaos engineering to it, right? So, if you run this application, probably one of the things that you might be wondering about is, okay, so what happens if things get a little bit slower on the networking? So let's say that, for example, I have a networking link in between my database and my server, just for argument's sake. That slows down by, let's say, I don't know, 100 milliseconds. And I'd like to know how that affects my application. Right? So this is something that we can do. This is something that you could do with TC, with traffic control. But if you are running in containers, there's a little utility that I would recommend using. It's called Pumbaa. If you go and look for that, look for Pumbaa, it's on GitHub. And it's a little wrapper around TC that makes it awfully easier to actually use rather than have to deal with that. And it does a bunch of things that are useful for chaos engineering. Can kill containers, can do other things to them. But the thing that we're going to be the most interested in right now is the NetM, which is basically wrapping the TC to introduce things. So if we just scroll down to the network emulation, the allowed things that are delay, loss, duplicate, and reorder, corrupt and rate, right? The delay is what we would like to look at right now. So using Pumbaa is pretty simple. I have Pumbaa pre-installed, but you can install it yourself by following the instructions from GitHub. I should have it in my path too. Yeah, so basically, if you look at what we're running here, we have the two containers. We have the container with Ghost, and we have the container with MySQL. And the selling point of Pumbaa is that it's actually letting you work on, sorry, let's switch back to the game, is that it lets you select the containers more easily rather than doing Docker PS and copying stuff around. So let's do an experiment. Let's say that we saw how quick it is roughly to access the website now. And let's say that we would like to check what happens if we add an extra delay of 100 milliseconds to the connectivity between the Ghost, the server, and the MySQL. It doesn't sound like a lot, so my hypothesis would be that it might probably increase by a double of that, just a guesstimate, if every request to the server results in one request, maybe two requests to the database. Let's say that would add 200 milliseconds. So let's do that, and let's try to implement that. So one of the first things that you want to do with Pumbaa is actually, well, before we even get there, so Pumbaa works by leveraging TC. It's a traffic control, and that's a utility that you can run in your host. But the TC has two problems. First is that it's not particularly easy to use. And second is that within containers, you have the virtualized network devices that Docker is creating for each of these containers. So you need to be able to select the right one. And Pumbaa makes both of these things very easy. So the downside there is that by default, Pumbaa is expecting your containers to actually have TC inside of them. And that is probably not the case, especially if you're working on creating the containers that are really small and as efficient as possible. So another way, a fortunate workaround, is that Pumbaa can actually start another container that has the TC installed, so the TC can modify the networking status there, and it can attach to the container that you want to start, to affect in a way that you don't have to have the thing pre-installed. Okay, so let's do that. So okay, so we have the two containers. One of them is called what is it called? Meower Ghost, and the other one is called Meower DB. Okay, so we can actually directly leverage Pumbaa, let them. And let's say that we're going to give a duration of 60 seconds. We're going to do TC image to specify the Docker image that the other container attached to the container we target containing the TC is going to be like. So we can specify any image that has the TC in the right place, but Pumbaa actually comes with one. It's Docker IP root 2. So we can specify that image. Then we want to specify delay. We want to add 100 milliseconds of the delay time. We don't want to add any jitter so that it's easier to think about. And we also don't want to add any correlation. So we're going to select 202. And finally, the name of the container. I could copy that too, but the nice feature of Pumbaa is that it actually lets you prepend the name with regular expression too. And so I can do meow db, and this way it should find my container for me. So before I run that, I'm going to open another new tab. So just like we did a minute ago, I'm going to rerun the AB to double check the steady state, and also have the other tab open so that I can use that to verify my experiment. So T to 10 seconds, a concurrency of 1. Ignore the length of the document, and we are calling 127.001 output 88. So let's just run that really quickly again. Yeah, this time it took a little bit less, 88 milliseconds, but still in the same ballpark. So managed 114 requests within 10 seconds. Okay, and now to our experiment. Let's try to add this for the 60 seconds. And let's try to rerun the same experiment again. Okay. So what I'm seeing here is that it took 167 milliseconds to the request, per request, and that we completed 62 requests, which is interesting. So let's see if that actually makes any sense. If we injected 100 milliseconds delay to the communications coming out from our MirrorDB, from the database or MySQL, and it added roughly 60 milliseconds to time per request, that would mean that not every request was hitting the database. Let's just double check that what we did actually worked with Pumbaa. So now that it's finished, let's rerun it again and see that we're back to the levels from the steady state that we initially wanted to. Well, initially saw, sorry. Now it's 132 milliseconds, so it looks like it didn't really work, so maybe I made a typo. Let's see, if we look at the Docker images that were finished with -a, you can see that Pumbaa did create 2 images, and this is how it works by basically creating that container ID, executing the tc command on it, and stopping. 45 seconds, so if you do docker inspect of that particular container, you can see what it did. So you can see the, for example, the command that it generated qdisk add dev ethernet 0 root net time delay of 100 milliseconds. That looks correct. And started at and finished at, so it only took about, was it 15 milliseconds to execute that, and it seems to have worked fine. Let's take a look at the other one. And just to kind of show you what Pumbaa did, to undo what it was doing, it basically did qdisk del of dev Ethernet 0 root netem. Okay, so why did we not see any slowdown? DB del core PS and spell. So Pumbaa netem dash duration 60 seconds dash tc image Gaia docker route. That must be correct because that would work. Time 100 T30 correlation 0 and RA2 So let me just double check the steady state again. Yeah, it's about 87 milliseconds. Okay, so let me rerun this just in case. Okay, finally, and let's see if we can get the same values or similar values again. Okay, so I think what happened is that I had run it too late. Because right now you can clearly see that the increase is dramatic. Instead of the 80 milliseconds that we saw before and about 100 requests or so that we had in the steady state, around 15, now we're getting only 15 complete requests, and the average is 692 milliseconds per request. So yeah, so that looks like almost half a second of increase in terms of the networking delay generated by the 100 milliseconds delay between the database and the server. So let's do just one more time to just make sure that the numbers are correct. So nothing, no failures running right now. I'm just gonna go again get the steady state numbers. Yeah, it seems to be reasonably stable at about 80 something milliseconds and about 115 requests that you can do. And I'm just going to run for 20 seconds the netem with 100 milliseconds here. And we run my numbers here. Yeah. So when I pre-run it previously, I was getting numbers around 500 milliseconds. I think because of the streaming, it might be taking a little bit of the CPU away from it. But the bottom line is that the 100 milliseconds that we added to the delay that we added between the database and the server doesn't translate into 100 milliseconds increase in the time per request on average. It doesn't translate into double either. It translates into a quadruple of that. So if we were, that's just kind of, you know, a very that's a big estimate, a big guess really. So if we were to be a bit more scientific about that, we'd play with different values. Let me just quickly do the same experiment with a value of 500. And let's see if we add half a second of delay, if we're going to see again quadruple of that value in the time per request, or if that's going to become something else. Yeah, so that seems to be even more than quadruple. Now it seems to be more like 5 times on the value. It finished here, so let me just double check like a good scientist. That will be back, but at 2.5 seconds per request, that's about 5 times longer than the delay that we injected. And now we're back to 100, and probably if we run it a couple more times, we're going to end up something similar to the 88 or something that we saw before. Close enough, 90. Okay, so what we did just now is with a simple one-liner, we're able to introduce latency between two components of a system, a very simple example system that we deployed, a blog server and its database, and by running a simple one-liner with Pumbaa, we're able to verify our hypothesis. Well, in this case, learn that the hypothesis was completely untrue, to scientifically check what the real impact of the failure in question really was on the system. Okay, so I think we're a bit beyond the time that we had allocated. I hope that you enjoyed that. I certainly did. This is fun, although I do need to get a few technical things out of the way for next time. So thank you for everybody watching this. Hopefully I showed you and I convinced you that it's really not that difficult to get started with chaos engineering, and it actually is quite fun to poke around things like Docker and verify your assumptions about that. And if there is one takeaway that I would like you to take from this, is that chaos engineering can really give you a lot of value for a very small investment in designing some meaningful experiments. And every time you think that your system is stable, there's probably an experiment that can run that is going to show you otherwise. And at the very least, it's going to make you more either sure that you're working, that it's working well, or it's going to show you how to improve the system. I'm hoping that also you enjoyed looking at a few little things that we covered, like Pumbaa. It's a nice little tool that you can use on any Docker containers that you run. And once again, I would like to encourage you, if you're interested in any of that, go get the Chaos Engineering book from Manning. It's currently in early access, so you can go and tell me off and ask questions and request extra information, everything that is within that book. So thank you very much for watching. I hope that was fun for you, and see you next time. Thanks.